Good morning children and welcome back to your chemistry class. So today in this chapter of electrochemistry we are going to study about Cauchy's law. So first let us understand what does this law say. We already know that any electrolyte, it is made up of what? Cations and anions. Clear? So we can say that the molar conductivity of the solution at infinite dilution of this electrolyte, this is always equal to what? The infinite molar conductivity of a cation, that is the cation ion, right? Plus it is also equal to the molar conductivity of the solution of the anion at infinite dilution. Right? Just take an example like the molar conductivity of NaCl at infinite solution. So let's take about this of NaCl solution. What does it contain? It is going to contain the molar conductivity of sodium ion at infinite dilution and molar conductivity of chloride ion at infinite dilution. So let's see this of Na plus, that is cation, plus the infinite molar conductivity of chloride ion at infinite dilution. Clear? Let's take another example like infinite dilution of aluminium sulfate. So this will be equal to what? 2 times molarity conductivity of aluminium ion at infinite dilution and 3 molar conductivity of sulfate ion at infinite dilution. Clear? So how can we define what is Cauchy's law? It means the molar conductivity of an electrolyte at infinite dilution, it is always equal to the sum of the ionizable cations and ionizable anions that are present in the electrolyte, and each conductance, it is multiplied by the formula unit present in the electrolyte. Clear? I hope this definition is very clear to you. What does the Cauchy's law definition say? That the molar conductivity of an electrolyte at infinite dilution, it is equal to the sum of the ionizable cations and ionizable anions present in the electrolyte, and each conductance is multiplied by the formula unit present in the electrolyte. Clear? Take another example. For example, let's take the infinite molar conductivity of say H2CO3, right, at infinite dilution. So here what are we going to see? We are going to see 2 molecules of hydrogen ions, 2 molecules of molar conductivity of hydrogen ions plus 1 molecule of molar conductivity of carbonate infinite dilution. So once again, the molar conductivity of an electrolyte at infinite dilution, it is equal to the sum of the ionizable cations and the ionizable anions, and each conductance, it is multiplied by the formula. Over here H2 units are there, so hydrogen ions are 2, carbonate is 1 ion, so 1 carbonate ion, the unit present in the electrolyte. I hope till here it's very clear. Now let us discuss about the applications of Cauchy's law. So let's move to the first time. To determine the molar conductivity of a weak electrolyte at infinite dilution, right? So if the conductance of the ionizable cation and ionizable anion at infinite dilution is given, then directly we use the method, right? For example, let's take ionic conductance at infinite dilution of aluminium ion and sulfate ion are 189 per ohm centimeter square per mole and 160 per ohm centimeter square per mole respectively. Okay, calculate the molar conductance of aluminium sulfate at infinite dilution. So, to determine the molar conductivity of the weak electrolyte at infinite dilution, if the conductance of the ionizable cation and anion, they are at infinite dilution, it is given, then we directly use the formula or the method, that is the molar conductivity of aluminium sulfate at infinite dilution, it is equal to what? 2 molecules of aluminium ion, right, at infinite dilution plus 3 molecules of molar conductivity of sulfate ions. So now let's find out the molar conductance of aluminium sulfate. This is equal to 2 into what is given for aluminium ion? How much? 189. So 189 plus 3 into how much for sulfate? Sulfate 160. So 3 into 160. So this becomes 2 into 189 is 378 plus 3 into 160 is 480. This gives us 858 per ohm centimeter square per mole. This is the molar conductance of aluminium sulfate at infinite dilution. So this is possible when the conductance of ionizable cation and anion both are given to you at infinite dilution. Then we directly use this method. Clear? But suppose if the conductance of ionizable ion is not given, then how do we find out? Then we use the indirect method, right? So let's take this example, like the values of molar conductivity of HCl, NaCl and CH3CONa at infinite dilution R for 20 per ohm centimeter square per mole, 125 per ohm centimeter square per mole, and 90 per ohm centimeter square per mole, right? Calculate the value of molar conductivity of acetic acid at infinite dilution. Clear? So here what do you see? We haven't got the conductance of the ionizable ions over here. So now over here, how are we going to find out? Let's see what all is given to us. The molar conductivity of HCl is given, that is 420 per ohm centimeter square per mole. Then that of NaCl is given to you how much? 125 per ohm centimeter square per mole. And the molar conductivity of sodium acetate is given how much? 90 per ohm centimeter square per mole. Right, now we have to find out the molar conductivity of the acetic acid at infinite dilution. So here the value of the conductance of the ion is not given to us. Okay, so let's see what are the ions present over here. Conductance of, what is the positive ion? H ion, right? Plus molar conductivity of the negative ion dilution is this. Okay, now we have to find out from what is given to us. So I'm going to rub off this question and I'm going to do the whole question from here once again. So just check the way I'm going to do it, because this much space is not enough to complete the question. The molar conductivity of acetic acid at infinite dilution is equal to the molar conductivity of H ion in the infinite dilution plus the molar conductivity of the anion, right, in infinite dilution. Now let us see what was given to us. We were given the molar conductivity of HCl in infinite dilution. So this is equal to H ion plus molar conductivity of chloride ion in infinite dilution. Okay, this is my first equation. Then infinite dilution, molar conductivity of NaCl in infinite dilution is equal to molar conductivity of sodium ion in infinite dilution plus molar conductivity of chloride ion in the infinite dilution. This is the second equation. Then the third was given to you. Which electrolyte was given to you? Over here it was sodium acetate, CH3COONA. This is going to give us the molar conductivity of which ion? Positive ion is your Na plus the negative ion molar conductivity in its infinite dilution is your CH3COO minus. This is your third, right? Now if you see over here, if we subtract equation 2 from the sum of equation 1 and equation 3. So what are we going to find over here? What did I say? If we subtract equation 2 from the sum of equation 1 and equation 3. Subtracting equation 2 from sum of equation 1 plus 3. Now when you do the whole thing, what are you going to get? The molar conductivity of H ion in the infinite dilution plus molar conductivity of CH3CO acetate ion in the dilution, infinite dilution. This will be equal to the molar conductivity of CH3COOH. Okay. Now, therefore, molar conductivity of the acetic acid will be equal to 420 plus 90 minus 125. This is equal to 510 minus 125. 385 per ohm centimeter square per mole. This becomes your answer. Clear? I hope this is very clear to you how to find out the conductance of the electrolyte at infinite dilution. Okay. Next we move to what is the second application. The second application of Coulom's law is to determine the degree of dissociation of a weak electrolyte. Okay, so we know that when we dilute the weak electrolyte, the degree of dissociation it increases and molar conductivity also increases. So suppose an infinite dilution, the dissociation of a weak electrolyte is say 100%, then the degree of dissociation will be 1 and the value of the molar conductivity approaches the limiting value. That is, what is your limiting value? The molar conductivity at infinite dilution. The molar conductivity at infinite dilution. Okay, upon molar conductivity of the weak electrolyte at infinite dilution. So we can also say that this is equal to molar conductivity of a weak electrolyte at concentration C upon the ions, the positive cation and the negative cation, the molar conductivity of the positive cation and the negative cation in the infinite dilution, isn't it? So we can write it down like this: plus V minus delta and conductivity, right? So the degree of dissociation of a weak electrolyte at a particular concentration can be calculated if all the values are given to us. Clear? Third point, to determine the solubility of sparingly soluble salt. To determine the solubility of a sparingly soluble salt, that is the molar concentration. This is equal to the specific conductivity of the saturated solution, right, into 1000 upon the molar conductivity at infinite dilution. Okay, so this can also be equal to what? This is equal to the specific conductivity of saturated solution into 1000 upon what is this? This is always equal to the molar conductivity of the cations and anions in the infinite dilution. So we can write it down like this: V plus molar conductivity of the cations in the infinite dilution plus the molar conductivity of the anions at infinite dilution. Clear? So over here M means molar concentration of the saturated solution of the sparingly soluble salt, right, which is always equal to the solubility of the salt, and the unit given to it will be mole per liter. This is the unit that is given to determine this molar concentration of the saturated solution of the sparingly soluble salt. So this was all about your Clausius law. Next we need to understand Faraday's law. So Michael Faraday, he established a relationship between the amount of product liberated at electrode and the quantity of electricity that is passed through the solution to carry out the process of electrolysis. I hope you all already know what is electrolysis. So what was the work of Faraday? Michael Faraday, he established what? A relationship between the amount of product that is liberated at electrode and about the quantity of electricity passed through the solution to carry out the process of this electrolysis. So according to him, he gave two laws. According to him, the first law says, Faraday's first law states that the amount of product liberated at the electrode is directly proportional to the quantity of electricity through the solution to bring about the process of electrolysis, right? So what is Faraday's first law? It says that the amount of product liberated at the electrode, it is always directly proportional to the quantity of electricity that is passed through the solution to bring about the process of electrolysis. So if W is the substance that gets deposited at electrode on passing suppose coulombs of electricity through the solution to bring about the process of electrolysis, right? So we can say that this Q is directly proportional to I into T, right? The current into time, and we know that the product or the substance getting deposited at electrode is equal to Z I into T, where what is your Z? Z is your electrochemical equivalent, right? And over here I, it is always measured in ampere, and your time is always measured in second, or it is equal to 1 second, and this is 1 ampere. Clear? And this, therefore we can say that the substance deposited at electrode is always equal to Z. If that is current flowing is 1 ampere in 1 second, then your substance that is deposited on the electrode is equal to the electrochemical equivalent, and this electrochemical equivalent, it is measured in grams per coulomb. This is the unit given to it. Okay, I hope this is clear. Now let's move to Faraday's second law. Now what does Faraday's second law of electrolysis states? It states that when same quantity of electricity is passed through the solutions of different electrolytes, okay, connected in series, the masses of substances liberated at the electrodes, they are directly proportional to their equivalent masses. Clear? So suppose if W1 and W2, these are the masses of the substances that are going to be liberated by passing the same quantity of electricity, right? And your E1 and E2, they are the equivalent masses respectively. Then what do we know? W1 upon W2 is equal to E1 upon E2, right? And if your W1 is equal to Z1 IT and W2 is equal to Z2 I into T, then we can also say Z1 upon Z2 is equal to I1 upon I2, isn't it? So we know that is directly proportional to your electrochemical equivalent. So this E is equal to Fz. What is this E equal to? Fz. Where over here your F, that is called as Faraday's constant. Faraday's constant, and it is equal to 96,500 coulombs, right? Then we should know that the substance that is deposited on the electrode is always equal to your E, that is the equivalent mass. Followed? So on passing 1 Faraday, the quantity of substance deposited is equal to 1 equivalent mass. 1 Faraday, as I have already told you, it is equal to 96,500 coulomb. So that's all for today, and with this we wind up with the chapter also. Certain numericals which are based on the formula has to be done, which I will be sending to you tomorrow. Thank you.